In this video, we're going to go ahead and cover section 9.1, sequences and series from Unit 9, sequences, series, and probability. This is a pretty cool unit. We have a lot of pattern stuff and uh, real world applications that go with them. We're going to go over kind of the basics. This is kind of a lengthy unit, 9.1. So a lot of the problems are worked out in advance, so just kind of bear with me, okay? Let's look at the first definition we have here. We have an infinite sequence is a function whose domain is the set of positive integers. So that means you can kind of think of it like this. X is going to be the positive integers. Okay, the positive, that remember this means integers. The function values are the following: ace of 1, ace of 2, and so forth all the way to ace of n. If we have, or I should say subscript, these are actually subscripts, okay? If we have dots at the end, that means the sequence is going to go on forever and ever. So it's like a pattern that just continues, okay? Where the numbers 1, 2, 3, 4 are the that term of the sequence. So this would be like the first term, the second term, the third term, and so forth. And you'll notice this is also the domain. So the first term is like x equals 1, if you want to think of it as a function, okay? Um, like I said, the terms of the sequence. When the domain of the function consists of the first and positive integers only, meaning if it just stops at this number, whatever it is, then it's considered to be a finite sequence. And that means that it's not going to go on forever. It's going to stop at some point. It'll look kind of like this. You'll have ace of 1 all the way to whatever number we decide to stop at, or the problem stops at, and that is the upper bound of the sequence. So no dots means it's finite. Okay, so it ends, it doesn't go on forever. Quick note, if we start with ace of 0, a subscript 0, then that means that the domain is also going to include 0. Okay, so let's go ahead and look at an example. This first one is worked out for us because it's actually pretty simple. It says to write the first four terms of the sequence a subscript n is equal to 2n plus 1. So the solution is basically just taking our numbers, so the domain, remember the domain is the positive integers, so our domain is basically the positive integers. So like 1, 2, 3, and so forth, okay? All positive. So we have, starting with 1, you plug in 1 into n. So a sub 1 is equal to 2 times 1 plus 1. You just, work it out. 2 times 1 is 2, plus 1 is going to give us 3. You do the same with 2, 3, and 4 because they want the first four terms. So subscript with 2, 2 times 2 plus 1 is 4 plus 1 is 5. With a 3, 2 times 3 is 6 plus 1 is 7, and so forth. And you can kind of see there's a pattern here in this one. We're kind of just going up by 2, right? So some of them will be as obvious as that, where you just have to kind of add or subtract something to get to the next term. So you'll notice that as our domain is going up, as we're going up by numbers here, as we're going up by 1 in our domain, 1, 2, 3, 4, we're going up by 2 with our outputs, with our sequence, okay? And that's kind of where this comes from. We have 2 times, so this number times the number we have here plus 1, and that's where this comes from. And so here at the bottom, I just kind of have it written out. Officially, the sequence for this would be 3, 5, 7, 9. If we stopped it there, then it would be finite. If we kept it going, then it would be infinite, okay? So that's it for the first one. Let's go ahead and look at another example. This one does have a lot of examples, so hopefully the video is not too long. Okay, we have alternating signs. It says write the first four terms of the sequence given by ace of n is equal to 2 plus, get that to focus, 2 plus negative 1 to the nth power divided by n. So I kind of started this one and we're going to finish it together because again, it's just the writing that takes forever. So you start off with a sub 1. So I just did my 2 plus negative 1 to the first power over 1. So wherever you have an n, you're basically plugging in that 1. So kind of like this. We have our 1 here, our 1 there, and our 1 there. And it's just matching up with the n's that we have up here. So a lot of just plugging in, yeah? So this is negative 1 to the first power is negative 1. 2 plus negative 1 is 1. Divided by 1 is just 1. So there is the first term of this sequence. Okay, let's look at the next one. We have a sub 2, so now we're thinking instead of the n, we're going to put a 2. So there's my 2's where the n's used to be, and this is going to give us, let's see, 2 plus negative 1 square is negative 1 times negative 1, which is just positive 1, okay, over 2. So 2 plus 1 is equal to 3. 3 over 2 is 1.5. And you can leave it as a decimal or fraction, does not matter for this one. Okay, so there's the second one, first one. Third one, I already have it written out for us. We have a sub 3. So again, this is now our third term. There's our n. So we have 2 plus negative 1 to the third power. You're thinking there's going to be 3 negatives, so it's going to stay negative, negative 1 over 3. 2 plus negative 1 is just going to be 1 over 3. So we have a third. And for this one, I guess I can do I already did decimal, so I'll just do a decimal. So 1/3 kind of goes on forever, so I do have to put those dots. Probably better to keep the fraction for that one, but that's okay. Let's do the last one for this one. We have a sub 4 because, again, we were looking for the first 4 terms, so we're going to plug in a 4. And we just worked that out as well. So we have 2 plus negative 1 to the fourth power. You're thinking you have an even number of these negative 1s, so it's going to stay positive. And then 2 plus 1 is 3 over 4. Since we kind of kept with decimals here, this would be 0.75. And that is it for that one. Okay, pretty simple problem. Let's look at a note that I have written down here because this is going to be helpful for the next one. It says for alternating signs sequences, try multiplying by negative 1 to the n power, negative 1 to the n minus 1 power, negative n to the n plus 1 power, some combination that looks like this. So the one we had up here was kind of like negative 1 to the n. We had this right here, and you'll notice that the signs here anyway, they alternated. We had a negative, positive, negative, positive. So they alternated. We're going to have our next example is going to include one that has, you kind of have to figure this out. So that's why I kind of gave you like a hint here. So let's look at the next problem. It's a two-part problem. Example number 3, it says finding the nth term of a sequence. So here you have the sequence and you have to figure out what the expression is. So in the 2 before we had the expression. For this one we don't. So let's see what we're going to do. You can kind of see in this one that you try to find a pattern first, right? See if you can find a pattern. I noticed that from here to here, I kind of see a plus. It's going up by 4. It's going up by 4. It's going up by 4. So there's going to be a 4 in there somewhere. To kind of make it a little bit more structured, what I would do is I would say, well, I know that this is a sub 1. This is a sub 2. This is a sub 3. This is a sub 4. So what I'm going to do is I'm going to make like a little chart. I'm going to put my domain on the top, which is kind of like our x, right? And I'm going to put the term value on the bottom, which is kind of like our y value. So the domain is this, so it's like the 1, 2, 3, 4. It's the number, it's the subscript is what it is. It's this part. 1, 2, 3, 4. Okay. And the term value is actually the value of a sub 1. So it's this right here. It's 1, 5, 9, and 13. So 1, 5, 9, and 13. And it does go forever, but we're just going to use what we have here to figure out an expression. This is kind of like x. This is kind of like y. Okay, so just kind of keep that in mind. If you were trying to find an equation that went with this pattern, what would you do? Well, you notice that since they're going by the same number, it's probably going to be something linear, yeah? So this right here implies that this is going to be something linear, which means that we can probably use our y equals mx plus b equation for this. So what am I going to do? I'm going to find the slope first. I'm going to go ahead and just pick two numbers, and I'm going to find the slope, which I kind of already know, but based off of over here, but let's find it. So we're going to take these two values, subtract them, which is 9 minus 5 over the x's, so 3 minus 2. If you don't know what I'm doing, I'm finding you don't have to write this down, but it's this part. M equals y sub 2 minus y1 over x2 minus x1. Long time ago, the slope formula, yeah? So that's what I'm doing here. This number minus this number, and then over this number minus this number. So 9 minus 5 is 4, 3 minus 2 is 1. So our slope is 4. Yay, which is what we kind of had over here. It's going up by 4, right? So that's going to be the rate that this is moving by. And after this, I would use my point slope formula. That seems like the easier one for me. Or you could use this one too, just plug in some numbers. I'm going to use this one because I just like this one better. And I pick a point, so I'm going to pick 1, 1 because it's the easiest one and plug everything in. So y minus 1 is equal to m is 4, x minus 1. So both of these are 1, so those ones are there. Work this out, we get y equals 4, x minus 4. You move that one over, so it's plus 1. So we end up with y equals 4x minus 3. And this is kind of the equation that gives us these values. So if you were to graph this, you would get the numbers 1, 5, 9, 13, and so forth for your output values. But we're doing a sequence, not exactly a function. So what I'm going to do is I'm going to rewrite this in my sequence notation. So the sequence would be that a sub n, so any nth term, kind of like the y, okay? Remember, it's the value here. It's all the a's. You want to kind of put like an arrow here, okay? Is going to be equal to 4n because n represents the term, not the term, but the number that we're at. Which term are we working on, okay? Minus 3. And this would be the expression that we're looking for, okay? That's it. That is it for that example. Let's go ahead and look at the next one. This one requires a little bit of thought, okay? So we have 2, -4, 6, -8, and that's actually the problem. That was the problem, and we just had to figure out the expression from there. But I went ahead and put a few notes here at the bottom. We have that this is ace 1, this is 2, this is 3, this is 4. And what I'm doing is I'm going to try to figure out how can I get from this ace of 1 to a 2 using some notation, okay? You'll notice that the numbers are alternating. We have positive, negative, positive, negative. So we're probably going to have to use something with alternating signs. We're going to have to use the alternating signs, which we kind of saw in the one before. So you can do -1 to the n, -1 to the n minus 1, etc. We're not just anyone's gonna work. We're gonna have to kind of mess with it a bit. Okay. So let's see. How do I get from using a 1? Remember, this represents n. The 1, 2, 3, 4 represents n. So with a 1, how do I get a 2? Well, I know that 2 times 1 is 2, right? So that works. With the 2, and here's what I'm doing. I'm kind of taking this number and plugging it in. I have to plug it in somehow. That's what I'm trying to do. The next one, well, I know that I need to get to a 4, so I know that 2 times 2 is also going to give me a 4. I can't just make it a -2 because that's not negative. So 2 times 2 is 4, but this is negative. So this is where this is going to come into play probably in a little bit. We'll come back to that. For the 3, same deal. 2 times 3 is going to give me 6. And then we have the same deal here, but it's -8. So 2 times 4 is 8, but I want it to be negative. So now we're going to have to figure out which of these little tricks over here is going to work to give us exactly what we want. So let's try the first one, okay? And I'm going to try it with the first 2 terms, and then if it works for those 2, I can try the next 2. It has to work for all of them, okay? Let's do 2 times 1 times -1 to the n power. So n is the 1. So let's see what that gives us. Let's see. 2 times 1 is 2. -1 to the first power is -1, which would be -2. So this one right off the bat is not going to work because those two need to be equal. So it's not going to be this one. Okay, so now let's try this one. So this is not a division sign, okay? It's like saying this or that. So I'm just going to make it a little bigger. So let's try this one now. So we're going to have, again, 2 times 1 times -1 to the n minus 1. So n, again, in this one is 1. So 1 minus 1. What is that going to give us? Well, let's see. 2 times 1 is 2. -1 to this power, remember, 1 minus 1 is 0. So it's kind of like saying -1 to the 0 power. And anything to the 0 power is just 1. So 2 times 1 times 1 is 2. So this one looks like it might work. It worked for the first one. Let's try it for the second one. 2 times 2 times -1 to the n minus 1. So again, my n for this one is 2. So 2 minus 1. What's that going to give us? Let's see. 2 times 2 is 4. And then -1 squared, okay, is, oh, I'm sorry, not -1 squared. We have 2 minus 1. So -1 to the power of 2 minus 1 is 1. Okay, so we have to subtract that first because you can't see the minus. There we go. 2 minus 1. Oh my God, it looks like an equal sign. Minus. There we go. -1 to the first power is just -1. So it's going to be 4 times -1, which is -4. And it looks like that works too. Let's do the last two real quickly. So 2 times 3 times -1 to the power of, now our n is 3. So 3 minus 1 is equal to, let's see, 2 times 3 is 6. -1 to the power of 3 minus 1 is 2. That gives us 6 times -1 squared is just 1. So we're good. And I'm guessing the last one's going to work too. Let's see, 2 times, I'm going to go kind of fast on this one. 2 times 4, -1 to the power of 4 minus 1 is equal to, 2 times 4 is 8. -1 to the fourth power, I'm sorry, -1 to, I keep doing that. 4 minus 1 is 3, right? 4 minus 1, 3. And since we have 3 negatives here, it's going to come out to -1, which gives us -8 at the end. So it looks like this is the way to go. So our expression then is going to be a sub n, because remember, we have to kind of generalize it. A sub n is equal to 2n, right? So I guess I should kind of put this in here. Let me put this in here. -1 to the n minus 1. That's what we multiplied by. Okay, so there we go officially. So 2 times n times -1 to the n minus 1 power. And that's it. Typically, these ones, they like to write them with the -1 first, so you might see it like this. But it's the same thing, okay? All right, that's it for that one. Let's move on. The next one is done for us because, again, the time. We have a recursive sequence is when a sequence is defined by previous terms, okay? So basically for this one, you need a few terms first before you can move on to the next one. So recursive example, it says write the first 5 terms of the sequence defined recursively by a sub 1 equals 6, and then a sub k plus 1 is equal to a sub k plus 1, a sub k, and then plus 1, I guess, on the side. The plus 1 is like normal sized. So what this means is that the next term is going to be basically this one plus 1. So it's the previous term plus 1, where k has to be greater than or equal to 1 because, well, that's what we started with. Okay, k kind of acts like n, so I just kind of put that note right here. Let's look at the solutions. It's actually not that bad. Let me see if I can. I guess I'll just kind of do this one thing at a time. Try to look at one thing at a time here. Okay, so we have, actually, let's do this. We'll use my tablet here. So solution, the first term is given. So a sub 1 equals 6. It's there. The second term. So the second term, we know that a sub 2 is equal to a sub 1 plus 1. There's that k plus 1 right here, okay? So all we have to do is we have to take the previous term, so a sub 1, and then add 1 to it. Well, a sub 1 is just equal to 6, so 6 plus 1 equals 7. Next one, same deal. A sub 3 is equal to, well, 3 is just 2 plus 1. That's where the k plus 1 comes into play. And we take the second term because it's the one before, and we add 1 to it. So 7 plus 1 is 8. Do it again for the fourth term, and you'll notice the same pattern. Just take this number, add 1. Once you've done a few of them, you can kind of figure out the pattern. This one's just basically adding 1, so the next one's just 10. And the sequence is just 6, 7, 8, 9, 10. So counting by 1, basically. And just go on forever because it didn't specify, so I'm assuming it's going to be an infinite sequence. Okay. Um, that's it for that one. There's really nothing else to go over for that one. Basically you use whatever's given to figure out the next terms. Okay. Let's look at a really cool example now. This is a pretty popular sequence. It's called the Fibonacci sequence, and it is defined by the following. A sub 0, okay, so now our domain is going to include 0, is equal to 1. A sub 1 is equal to 1, which is kind of weird because they're both equal to the same thing, right? And the next terms, let's get that to focus a little bit. The next terms are basically a sub k is equal to a sub k minus 2, so 2 terms before, plus a sub k minus 1 plus the term before. So this term, or not this one, the second term is going to depend on these two, basically. We have to write the first 6 terms. We do have to start at 2 because, well, we need those ones before we can start there. So let's see. A sub 0 is given, it's just 1. So is a sub 1. I'm just copying it. A sub 2, we're going to use the formula. Okay, so it's equal to a of k minus 2. So my k in this one is like the 2. So it's going to be 2 minus 2 plus ace of 2 minus 1. So I'm just taking my k's and plugging in the 2 that I have here, okay? Which is equal to a sub, let's see, 2 minus 2 is 0, 2 minus 1 is 1. So we have a sub 0 plus a sub 1. And we have that. It's just right here, 1 and 1. So 1 plus 1 equals 2. That's the answer for the second term. Well, I should say third term because we have the sub 0 here. So next one, we have 3 minus 2 now. And then 3 minus 1. So ace of 3 minus 2 is going to be ace of 1. Okay. Ace of 3 minus 1 is going to be ace of 2. So we look at the first one, it's equal to 1. Ace of 2 is equal to 2. So this one's equal to 3. Okay. Next one, ace of 4 minus 2 plus ace of 4 minus 1. Again, I'm just taking my number and plugging it into where the k is. That's going to be, let's see, ace of 2. 4 minus 2 is 2 plus ace of 3. So I look at the second term, so 2 plus the third term, 3, which is 5. And you should kind of see, I mean, you should see the pattern there. You're just basically adding the 2 before, right? So ace of 5 would be ace 5 minus 2 plus ace of 5 minus 1, which is ace of 3 plus ace of 4. So 3 is 3, and then 4 is 5. That's equal to 8. And the sequence, if you kind of want to see it a little bit more visually, because it's a little easier when you see this, is 1, 1, 2, 3, 5, 8. Can you guess the next one? We just got to add the 2, right? So 5 plus 8 would be 13. 8 plus 13 would be 21, and so forth. Pretty cool, pretty cool. This is a pretty good one. So if you have any time and you want to just kind of look more into the sequences, look up this one. It's a pretty interesting sequence, has a lot of different things that go with it. Let's look at another definition. We have the n factorial. This is kind of a fun one. I like this one. It's defined as n exclamation mark. So this exclamation marks means factorial. So this right here is a factorial. It's just an exclamation mark. So it looks like the following. If you have numbers being multiplied, basically it goes all the way up to whatever that n is. So if this was like a 5, it'd be 1, 2, 3, 4, 5. You multiply all of them, 1 times 2 times 3 times 4 times 5. That's it, where n is, again, a positive integer. Remember, this right here means positive integer, positive whole number. Think of it that way. Okay. Let's look at an example. And these are kind of cool because you can really you can, I guess, make a lot of things equal to 1. So let's see. 4 factorial times n plus 1 factorial over 3 factorial n factorial. So what are we going to do? We're going to try to rewrite this. Let's see. 4 factorial is the same as 4 times 3 times 2 times 1. That is this part right here, 4 factorial. You basically start with the number and you go backwards all the way to 1. Okay. And then we have, so I'm going to put that kind of in parentheses. Then we have n plus 1 factorial. So that's interesting because we don't have a number, right? We just have n and n plus 1. So think of it this way. If you're going backwards, well, you're going to start with n plus 1, right? Because that's what we have to start with whatever's in here. And if you go back 1, you're kind of subtracting 1. So 4 minus 1 is 3. So if I subtract 1 from this one, I just get n. N plus 1 minus 1 is n. And that's it. That's what I have on the top. Let's look at the bottom. We have 3 factorial, which would be 3 times 2 times 1. Oh, not 2, times 1. Getting a little ahead of myself there. Okay, so 3 times 2 times 1, and that's this part. Okay, and then we have n factorial. So n factorial is just going to be n because we don't really have anything else with it. We don't know what n represents. So it's just n. Okay, n times 1 if you want. You can do the times 1 if you really want. All right, so what can we do? Well, we can get rid of the n's, right? Remember, that's just n, so the 1's not really there. We can also get rid of the 1's here, the 2's here, the 3's here, which leaves us with 4 on the top times n plus 1. And there's nothing on the bottom, just a 1. So this comes out to 4, distribute 4n plus 4. And that's basically it, guys. That's it for the factorial. Nice, easy one. I forgot to mention the 0 factorial is equal to 1. So if you did have a 0 factorial somewhere, you want to put a 1 right away. Okay? All right, let's move on to the next example. We are almost done with this video. It's kind of lengthy, I know. It's just a lot of information. We have the summations. So a summation is basically a sum of the terms that we have of a sequence. So we did in this up to this point are just basically here's the pattern, try to find the next number or try to find the expression that goes with it. So this one is actually going to take that pattern and add them up to a point. You can either add up to a certain number, so like n, whatever that number is, or you can do it infinitely, which we'll show you in just a bit. You have some definitions here that says the sum of the first n terms of a sequence is represented by the summation, so this like weird looking E thing is a summation from 1 to n, where basically I is the index of summation. It's kind of like the starting point. So this part right here, this right here, it's the beginning value. So it's where are we gonna start adding at what term? So in this case, it's the first term. N is the upper limit of the summation, meaning it's the last number we're going to look at. So if it was like from 1 to 5, you would just do the first 5 terms, add them up, okay? And 1 is oh, there should be an I. An I is the lower limit of summation, okay? Well, I mean, I guess it could be 1 in this particular, we'll leave it as a 1, I guess. In this particular notation, we could say 1 because that's the first term, okay? So 1 is the lower limit of the summation. So let's see how it works, and it won't be that bad, I promise. We have the first example. It says so the sum from 1 to 5 using this expression, 3i. So what we're going to do is we're going to write my function 3 times, and start with the very first term, so 1, plus 3 times the next number, 2, plus 3 times, what's after 2? 3, all the way till we get to 5. So plus 3 times 4 plus 3 times 5. And that's it because we're going from 1 to 5. So we should go from 1 all the way to 5. And we just, multiply and add. So This would be 3. Let's see, 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. And we just add all that up. So 3 and 6 is 9. 9 plus 9 is 18. 18 plus 12 is 30. 30 plus 15 is 45. And that is it. There's our first smiley face of the notes, okay? Next one, letter B, we have another summation. So let's take a look at that. We have from 1 to 4 this time, and it's the same deal, but now we just have a little bit, a little bit more going on there. So let's do that. We have 4 times 1 plus 1, and I'll put it in parentheses so you can see the different ones, plus 4 times 2 plus 1. There's a second one, plus 4 times 3 plus 1. There's the third one, and I can fit this one here. Plus 4 times 4 plus 1. Work it out. So that's going to be 4 plus 1 is 5. 4 times 2 is 6. I'm sorry, 4 times 2 is 8, plus 1 is 9. 4 times 3 is 12, plus 1 is 13. And then 4 times 4 is 16, plus 1 is 17. So let's add this up. We have, I'm going to go backwards just because I see some easy addition here. 17, 13 is 30, plus 9 is 39, plus 5 is 44. Okay, last one. Hopefully I did the math right. If not, let me know. Last one we have here, and then we have one more after this, but it's already worked out for us. We have a summation with factorials now, so it's the same type of problem, but now we have to do with factorials. So from 0 to 8. So I'm thinking 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial, and I think you get the idea, but you just go all the way to 8 basically. Okay, and we just figured that out. So remember that this one is just 1, so it's going to be 1 plus 1, because 1 factorial is just 1, plus, let's see, 1 over 2. 2 factorial is going to be 2 times 1, so you're thinking 1/2. 3 factorial is 3 times 2 times 1, so 1 over 6. This one is 4 times 3 times 2 times 1. So 6 times 4, 24. You kind of get the idea, right? This one would be, oh my gosh, 24 times 5 is going to be, let's see, 5 times 4 is 20, 5 times 2, so 120. This one is 6 times that, so 720. You can kind of take it from the one before. 7 times that. Oh, we're getting kind of big numbers here. 7 times 2 is 14. Carry the 1. So 5, 50, 40. And I'm almost out of space here. 1 over 8 times this. Oh, wow. Okay, so 8 times 4 is 32. 8 times 5 is 40. So something really humongous like that, yeah? And you would just add this up and, get a decimal value. It looks like it's going to be pretty close to, let's see, 1, 2, 2.5. It's going to be close to 3, I think, because these numbers are going to be really, really small. So I'm going to say it's going to be close to 3. And you can check this if you'd like. It's going to be really close to 3. It's getting close and closer to 3. Let me know. Let me know about this one because I don't want to take more time with the calculator. Let's go ahead and do the last part here. We have properties of sums, just a lot of stuff to copy. Basically, if you are multiplying something, you can pull that number out and just multiply it times the number, okay, times whatever the end term is, where C is a constant. If you are, oh, I'm sorry, yeah, I'm sorry, exactly what I just said. This one, same deal. We can pull the constant out to the front and then do the summation and do it that way. For the third one, if you are adding two different things, you can separate them. So you can actually do this sum first and then this sum, and then just add them together. And the same goes for subtraction, okay? Last but not least, we have a series. So a series is basically a sum that will stop at some point, or it's kind of like a partial sum. So let me kind of just read it and see if that makes sense. If we have the infinite sequence, so we have our list of numbers, okay, then the sum of the first n terms of the sequence is called a finite series. So kind of like what we did right now, with these other numbers, if we stop it at one point, it's a finite series. In other words, there's no more dots. We're just saying from here to here. So the ones we did over here actually are finite series because they stopped it at some point. The second part here we have the sum of all the terms of the infinite sequence. So now we're talking infinite is called an infinite series and is denoted by the following: all our terms being added together, and on and on and on and on forever. And these ones are usually going to get closer and closer to some number, okay? Kind of like the last one we did, but that one is going to end somewhere. I'm not really sure. I'd have to check the decimal values for those, but if it did go on forever, then it would be considered one of these, okay? Let's look at the last example, and I know this video is kind of long, so sorry. You'll have a lot of time to copy, I promise. Example number 8 is done for us. It says for the series 5 over 10 to the I power from 1 to infinity. Find the fourth partial sum and, letter B, the sum. So we're going to do two things. We're going to find a finite series, which is the up to 4 basically, and then the infinite series, which is the sum. So here it is. We have for the fourth partial sum, basically you're going to take from 1 to 4. So where my I is, I put a 1, 2, 3, 4, which gives me the following. So 10 to the first power is 10, 10 squared is 100, and so forth. If you plug these in, well, actually, let's reduce them first. So if you simplify these, we get 1 half, 120, 1 over 200, 1 over 2000. And if you plug that into the calculator, you get basically a decimal, 0.5, 0.5, etc. A total of 4 5s because that's where we stopped. So 0.5555. And this is the answer for this one because it stopped at that point. Okay. This would be considered finite, but it's also a partial sum because we stopped there. We say it's partial because the actual summation does have the infinity sign. But we're just thinking about those first four. It could be considered finite. And last but not least, this is the last one that we're going to do in this video, the sum of the series. So the sum of the series means take everything and add it up. So we start with a 1 and we kind of go on forever. I just kind of copy what I already had up there. I know that this is going to be equal to 0.5, this is 0.05, and the zeros just kind of keep getting added. So in the end, we're just going to have a whole bunch of 5s. It's going to go on and on and on and on, repeating decimals, which happens to equal to 5 over 9. Kind of a side note here, if you do have this pattern, basically what's going to happen is you just take the number, whatever number is being repeated, and you put it over 9. So 0.888 is equal to a over 9. So if this was like 0.22222, it would be 2 over 9. And there is a proof for that, which I'm hoping to go over in class, maybe on Tuesday or Wednesday. So if we do get time to go over it, I know my number sense kids would like to see this, maybe. Here's part of the proof. So go ahead and just copy that, and hopefully we can get to it. It does relate to a little bit of something called geometric sequence, which we'll see in a later unit, but it's a pretty cool proof. So there you go. Hopefully it wasn't too long. You guys have a great rest of your day. If you have any questions, you just let me know. Thanks.